All right, for question number 4, you're given these two descriptions. This is probably my least favorite of these problems. There's not enough detail in some of this stuff, and the wording of the questions are just unnecessarily confusing. So student A says that the marble launched at 70 degrees will go further because it goes higher and spends more time in the air, therefore giving it a chance to go further. And student B says the marble launched 20 degrees will go farther because the horizontal component of its velocity is greater. And then we're supposed to, first for A, explain what aspects of A is correct, and then kind of explain how I arrived at the situation. So just kind of reason our way into saying what's correct here. Well, if so, at a higher angle, the projectile would spend more time in the air. So much. The projectile would spend more time in the air and go higher. Okay. Which would allow for it to travel horizontally further, but it does not have as great a horizontal velocity as the one at 20 degrees. Okay, it doesn't actually ask us to explain what's wrong with it, but it just doesn't feel right if I don't at least mention it. Okay. And then for this one here, it actually asks us to figure out to explain what's incorrect for student B. It almost feels like favoritism, but in this case, you would say they say that at 20 degrees they'll go further because they're a horizontal component of its velocity greater. Student B does not address that at a lower angle, the time of flight would be lower, thus not allowing it to travel horizontally for as much time as the 70-degree projectile can. Right? I'm not saying that it goes further, but it doesn't have as much time to do that, even if it could. Right? So derive an equation for the horizontal range of the projectile based on its initial velocity and angle of launch. Use the equation to calculate the horizontal ranges for the angles stated above and explain our results. I'll explain it here where it really gets unpleasantly confusing to answer this question, but I think it's kind of an okay exercise as far as derivation goes. Since we're not that used to doing objects at an angle, right? So just to reinforce this, if you have a velocity like this and you have an angle theta, then I can break down the components of this into x and y. So this would be my x component, right? And that would be v0 cosine theta, right? Cosine being adjacent to the angle. And then I can have the one in the vertical vy being v0 sine theta. Okay, so that's important to know because we're trying to calculate some stuff in the x and the y direction, and we don't really have anything to go off of here, right? We have very little to work with. So I'm going to write the two equations that are going to be relevant here. The velocity equation, which is v0 plus at, and then the position equation, which is x0 plus v0t plus 1/2 at squared. Okay. These are the general form of these equations, but we're going to actually modify them a little bit to use with the range situation here. First of all, we need to know time. We need to know how long it's going to be in the air to figure out anything else. The reason is that t is sort of like a vague, it's like an undefined variable here, right? So we know that it'll only be in the air for some time, and then we need to kind of be able to estimate that. So what happens is that, any object, again, launched in an angle like this will have this parabola. At the halfway point where the velocity in the y direction is 0, right? That's also the halfway point as far as time. So 1/2 the total time of flight is where that thing reaches its highest value, right? And so the total time it's in the air would be the time of flight, right? And so halfway is when it reaches its peak. And then halfway is also when the y value for velocity is equal to 0. So I can use this first equation. I can say, well, when does the velocity in the y direction equal 0? It equals 0 when my initial velocity, v0 sine theta, minus, and the reason it's minus because my acceleration is negative g times t, right? So this is the time when the final velocity is 0 in the y direction, right? So I can solve this equation for time, and it becomes v0 times sine theta divided by g is equal to the time. That's how long it'll take to get to that vy equal to 0 situation. So really, this is my half time of flight. Okay, so double that would be my total time of flight, and that's the time I would plug into my other equation, right? If I want to know the range, I would look at x. My initial position would be 0. My initial velocity in the x direction would be v0 times cosine of theta. So in the x direction, it would be cosine of theta times the time, which I know is going to be 2 times the time of flight. So 2 times that value there. Okay, so 2 v0 sine theta over g. And then there's no acceleration in the x direction. So those are the only terms that I have to worry about. So I have to simplify this. Becomes 2 v0 squared cosine theta sine theta over g. That's my range equation. And I know this one is not pretty, but at least it shows you some consideration about this kind of thing. Okay. Looking at D, you're given these two graphs. You're asked to calculate or to explain what might be wrong or right about these. They both have constant velocities, which are correct. So just kind of bullet point here, constant velocities for both. What's incorrect is that because V1 is the 70-degree one, it would actually have a lower horizontal velocity. Okay, basically its horizontal velocity would be shorter than the one shot at a lower angle, right? So V1 should be less than V2. Okay. And outside of that, I don't think there's anything else worth mentioning here. On the axis to the right, make a sketch of the vertical velocity of each marble. This one can also be kind of tricky. The vertical velocity, right, in the beginning is larger for the 70-degree angle, right? Whereas for the 20-degree angle, it's smaller. So we know that our starting points are going to be different, right? So for the 70-degree angle, we're going to start higher. It's going to accelerate downwards because gravity is going to pull it down, and eventually it's going to start moving in the negative direction. And if it follows a parabolic curve, it should hit basically the same velocity, but in the negative direction like this, right? And then the other one should start lower on the y-axis and then also accelerate downwards at the same rate, so at the same slope, okay. But it should not. It's really trying to get these two lines parallel. I don't know how effective this is being. I think that's it. Okay, so this is going to be for B2, and this is going to be for B1. B1 starts at a higher vertical velocity and travels in the air longer, so it's in the air longer, and so it has more time to kind of switch directions and values. B2 doesn't stay in the air as long, but its values are lower in magnitude, right? But they both have the same slope, which is, I think, what's most important in these two graphs. That and just knowing which one should be higher than the other. Okay, and that is it for that one.